Jrobot Self Drive, powered by Tensorflow Lite.
Hello everyone, welcome to Jrobot Self Drive, episode 3 of the Jrobot series. Before we get into Self Drive, let's look at how Jeribot has evolved over time. This is Jeribot in episode 1. We did the test drive in a local school. The video is available on YouTube channel. And in episode 2, we get Jeribot to do pizza delivery. And it delivered a pizza from a local pizza shop. For both episode 1 and episode 2, we rely on Jcontrol. This is a camera view available on Jcontrol for the human driver to control the robot car remotely via either Wi-Fi connection or mobile 4G network. And for both episode 1 and episode 2, this diagram summarizes the Jeribot system. It comprises of Jcontrol side and Jeribot side connected using 4G or Wi-Fi. To do self-drive, we have to get rid of Jcontrol altogether. And this is the system diagram like for Jrobot self-drive. Camera sends the image to Android. Android sends the command to Arduino. Then Arduino sends the command further down to the motors. The key part of it is a AI black box that's able to take a camera image as an input and spit out the steering angle as an output. This leads us into machine learning. We have a supervised learning problem. We need to define a model and collect data and train the model. After training, we convert the model into Tensorflow Lite and run inference or prediction on board Jrobot. For model building, I use Keras as front end and TensorFlow as back end. For myself, I find it easier to use Keras than TensorFlow directly. We need TensorFlow Lite. TensorFlow Lite allows us to do onboard inference using a trained AI model on a mobile device. I would say TensorFlow Lite is the key that makes this project work. Google provides this nice tutorial on how to use TensorFlow Lite, from converting the model into TensorFlow Lite to use it in an Android application. For model building, I haven't done much experiment. For this project, I simply adopted the well-known Nvidia CNN self-drive model. This is the diagram of their model. 5 convolutional layers followed by 3 fully connected layers. And this is my replication of the Nvidia model. 5 convolutional layers followed by 3 dense or fully connected layers. There is no max pooling and no dropout. And the summary shows I got around 250,000 parameters to train. Before we can start data collection, we have to define the use case of Jrobot. It's not a simulator. We're training a model to work on a real device in a real environment. I'd love to have Jeribot run on the open road, but we're not allowed because Jeribot is too slow and too small to share the road with other cars, and because it doesn't have any license. Jeribot will not be able to run on bushland, grassland, natural streets, because these are too many variables. This is our user case. Jeribot is a concrete footpath traveler. Now we get to the actual training. I trained Jeribot on footpaths using Jcontrol, with additional features to record camera image and steering angle at a set frequency. Nvidia used 10. Jeribot is a bit slower, so I settled down to 3 to 5. For many other AI problems, data is the bottleneck. But for Jeribot, as long as you want to invest time, you can get unlimited data. A frequency of 3 will give you 10,000 data points per hour. I trained Jeribot around the neighborhood and collected about 30,000 data points. With all the data collected, we need to do some pre-processing and data augmentation. This is the image from the Jcontrol. Focus on the front camera view. We get rid of the trees and skies, and then resize to the 66 × 200 the Nvidia model specification. And then I remove the color and become grayscale. I reckon if I can drive Jeribot using a grayscale image, the AI model should be able to. And for data augmentation, a popular approach is the horizontal flip, but this is not possible in Jeribot case because the mounting point of the camera is to the left of the center line, so I cannot flip. But there are other ways we can do image shift. This is the original image. We can shift the image a little bit to the left or a little bit to the right, and we can adjust the steering angle accordingly. So that way we basically increase our data size by a few folds. These are the sample data points. Line blurred, sun glare, shading on the ground, line markings, and path turning. And the Jeribot can sway from side to side. Now we're ready to train the model. The only thing I would say is it is slow. This is the training log. And this is the chart of the training log. I take the model at epoch 27 since the validation loss does not improve much from there. Next, we need to convert the trained model into Tensorflow Lite. As we said, Tensorflow Lite is the key part of this project because it allows us to do onboard inference on a mobile device without a need for a data connection to a server, like in the case of TensorFlow serving. There's also something called TensorFlow Mobile that does the similar thing, but I believe TensorFlow Lite is a newer and better approach. Because we have defined and trained our model in Keras, so we got a Hi5 file. So the conversion to TensorFlow Lite is in two steps. First, we go from H5 into TensorFlow PB file, and then from PB file into TensorFlow Lite file. We use a Python script to do the first step conversion from H5, Keras H5 into TensorFlow PB. And then we use a command to convert the PB file into TensorFlow Lite file. This is how we use TensorFlow Lite file in an Android project. First, we initialize the TensorFlow Lite interpreter. And then we do the image pre-processing here. Crop, resize, and convert to grayscale. And we feed the image data to the TensorFlow Lite and get a steering angle from the output. After all the hard work, here comes the moment of truth. Does it actually work? In the next part of this video, I'll show you Jrobot Self Drive start menu, screen settings, and we will do test drive at 2 different locations.
To start Jrobot Self Drive, we first stop Jeribot car. Next, we run Jrobot app on the mobile phone. On the phone screen, you'll see BT is the Bluetooth connection between the phone and the car. CamF is the frequency of the camera and the same frequency used for TensorFlow Lite and control of the motors. USB is the ultrasound brake function. Gear is the maximum power of the car. Down below on the display we also have ML and MR. They are the level of power delivered to the left motor and right motor. The start button is on the top, but before we can click on it, we have to put the phone on into the phone box. It's a two-hand operation. Now the phone is sitting in the box. We go to the back of the Jrobot. Put a finger through the hole on the phone box and touch the start button, and the Jrobot will start moving. Here we do a small test before the real road test. We put the Jeribot on the stand and start it. You can see the wheels start turning. And on the phone, you see the reading of ML and MR. That's the power to the left motor and right motor. So when we align the J motor to the footpath, it's almost going straight. Now if we turn Jeribot to the left, you see the MR start to drop, and it will force the car to go to right. Similarly, if we turn the Jeribot to the right, ML will drop and the car will turn left to compensate. So that shows Jrobot Self Drive, the black box model, does work after training.
This is test drive number 1 on a footpath around a residential block. Because there are people around, I put Jrobot on a dog lead. This is test drive number 2 on the curvy footpath in the local school. As there is no one around, I let Jeribot run free. I hope you liked the test drive videos. They clearly showed that after training the AI model does work, and Jeribot is able to follow the footpaths. But to me, it feels like a half-trained dog. I had to pull the string and make it turn left or right at a few occasions, at corners or intersections, which is actually a need for decision making rather than the fault of AI neural net. If we go by the levels of vehicle autonomy, based on the fact that I only have to pull the string a few occasions, I guess Jrobot can sit at level 3 with limited self-driving. After this project, on my to-do list, I want to do some experiment with models to see if there are models that can perform better in the particular use case of Jrobot. I also want to expand the scene for Jrobot. Instead of on footpaths in a suburb, can Jrobot run on footpaths in busy cities, train stations, and other public space? And the harder question is, how do we train Jrobot or retrain it? I wonder if there's a way to do the retrain on board the mobile device. We'll probably get out of the domain of supervised learning into unsupervised learning or reinforcement learning. And lastly, if AI neural net cannot get us to full self-drive, then we look at the consolidation of sensors, other sensors, and controls. This is a summary of all the sensors and controls available for Jrobot. Camera and Tensorflow Lite is the key to maintain Jeribot position on the path. Ultrasound adds another safety layer for obstacle avoidance. Compass and GPS can guide the robot from a waypoint to the next. I haven't mentioned solid-state LiDAR. Definitely want to try when it becomes feasible in cost. On the control side, we used to have steering wheel on Jcontrol. In this episode, I use string control a dog lead, which is not ideal. I do only want to showcase the power of self-drive. The great thing is the AI model works so well that Jeribot only needs occasional control from a human driver. Although this is not full self-drive, it makes the control much easier, and it means other control methods like gamepad or voice control become possible options. All this control can be connected directly to Jeribot by Bluetooth. That will give a range about 5 meters. Or they can be connected to Jcontrol, which is then connected to Jeribot by Wi-Fi or 4G mobile network, which means unlimited range. And 5G is coming soon, and that will make Jeribot even more useful. There's so much flexibility in Jeribot and so much more to do. That's all for Jrobot Self Drive. Thank you for watching. My name is Joe. You're welcome to subscribe to my YouTube video or contact me. I'll see you in the next episode, but for now, Jeribot want to go out for a walk again.